Welcome to Scaling Up, the podcast where we scale up on knowledge so we do not scale up our systems. Hello, Scaling Up Nation. Trace Blackmore here, the host for Scaling Up H2O. And Nation, thank you so much for writing in, for calling in, for sending me voicemails, for doing all the things that you do to let me know what you want me to talk about on Scaling Up H2O. Now, a couple of weeks ago, I received some questions about scale, and the show primarily dealt with how we talk about scale to our customers. Well, I've received some more questions going into exactly what scale is. And simply put, I am going to try to boil down, no pun intended, what scale is when we're looking at something like calcium carbonate. Now, calcium carbonate is a common scale that us water treaters have to deal with. And if you've taken a class from me, you know that I call calcium carbonate the water treater's nemesis. Calcium carbonate is a combination of 5 things. And I'm just going to go right into an explanation of what those 5 things are. So we have alkalinity, hardness, pH, dissolved solids, and temperature. If you have listened to earlier shows, you have heard me speak on stability indices, and there's 3 of them out there. There's the Langelier, there is the Risner, and there is the Pecorius. I used to call it the practical, but we lost Paul Pecorius very recently, and I'm honoring Paul by calling it the Pecorius Scaling Index. That being said, they all put a little spin on how water is either dissolving or precipitating calcium carbonate. And depending on which one your company uses and that you're familiar with, it really doesn't matter which one you use. I get the question all the time, which one is better than another? They all do the same thing. They just have a different mathematical spin on how they get that result. So whatever one you're comfortable using, that's the one that you're going to use, but they all do the same thing. They start with the saturation pH, and that is exactly what I said before. That means we are neither precipitating or we are neither dissolving calcium carbonate. It is in equilibrium. With that, then one of those scaling indices will then put their spin on it, and they will say how scaling or how non-scaling the water is. Now, I did say non-scaling. I did not say how corrosive the water is, because Nation, all water is corrosive. So when we say it's either scaling or corrosive, that's not a correct way of saying that. Water's the universal solvent. It only knows how to do one thing, and that is to dissolve, i.e. corrode. So we know that waters are either scaling or non-scaling. They have one of those tendencies. So the 5 things that creates calcium carbonate are the 5 things that go into the scaling indices. Those are alkalinity, hardness, pH, total dissolved solids, and temperature. So if you're interested in learning more about alkalinity, I recently did a show on alkalinity. I talk all things alkalinity. That was episode 86. So go to episode 86 and you can learn about alkalinity. Also, if you want to learn about pH, I did a show on pH. That was episode 84. And Nation, those were because of questions that people in the Scaling Up Nation wrote into me, so I decided to do shows about that. So the other thing, one of the 5, so we talked about alkalinity, we talked about pH. Now we're going to talk about hardness. So this is the calcium in calcium carbonate. How much do we have in there? And that's going to go into the equation. The next thing we have is total dissolved solids. And I want to take a second and talk about total dissolved solids, because a lot of water treaters misunderstand what that is. Is total dissolved solids and conductivity the same thing? Well, no, it is very different. However, when we are looking at the multiplier that we use in figuring out if water is either precipitating or dissolving calcium carbonate, conductivity, or in this case, total dissolved solids, is such a small factor, we're not going to see very much difference if we interchange those numbers. So that being said, it is perfectly fine to use conductivity as a substitution for your total dissolved solids numbers when you're using these scaling indices. However, it is very important for you to know that those are not the same thing. If you're doing some other testing and you substitute the wrong number, you will not get the correct data. So you have to know what you're looking for, and you have to know what they're actually asking for within those particular equations. If you're wondering what the difference is, total dissolved solids is actually a weight test. We're going to take a sample that's mixed and filtered through a pre-weighed filter paper, and then we are going to evaporate all the water off of that filter paper. Once that's done, we are going to re-weigh the filter paper. We'll subtract out the original weight of the filter paper, and we will then know how many total dissolved solids are in the area that we are measuring, and that's that test. Now, conductivity is just the sum of the parts. It's actually measuring how much an electrical current, or how easy an electrical current can go from the anode to the cathode. And the easier it is to pass that charge from one to the other, the higher the number is going to be. Now, if you were to do conductivity in distilled water, and if you were to build your own conductivity meter by having an electrical charge going across, and probably everybody has seen that demonstration where somebody has a light bulb in there and they use distilled water and the light bulb does not light up, so then they dissolve some salt in it and the light bulb lights up. That's conductivity. That's being able to conduct that current across the water. The higher the number, the easier it is for that conductance to happen. Now, total dissolved solids, you will see on most meters right underneath the conductivity button, there is a TDS button. Folks, a little elf does not come out of your meter and do the test that I described and weigh it for you. It just takes a percentage of conductivity and puts that on your meter output. I believe it's right around 60%. It might be a little different between manufacturers of meters, but all it's doing is a mathematical calculation saying I'm going to take a percentage of the conductivity. So now the question comes up, which number do I use if I just use the meter? I understand I'm not going to do the weight test, but now I have a button that says conductivity and I have a button that says TDS, or total dissolved solids. Which ones do I use in my stability indices? And folks, again, it's such a small number, it doesn't matter. Now, if you're taking another test, as I just said, you might want to use that. But again, that is not doing the test the way the test has meant to be done. And there are a couple of reasons out there that you would want to run the actual weighted method of TDS, because that's how you run TDS. But for this show, I can think of no reason for you to do that. Now, the last part of our equation deals with temperature. And folks, calcium carbonate is the water treater's nemesis for this reason. We are water treaters, which means we are heat transfer efficiency managers. Our job is to make sure that all the heat that we're trying to transfer through that equipment takes place as efficiently as it possibly can. And scale acts like insulation, which means it's holding heat in. We said that that was great in your attic, but it's not so good in your heat transfer equipment, because that means the chiller has to work harder. We talked about this last time. The chiller has to work harder in order to overcome that insulation, and that's what scale is. Scale is insulation. So when it gets hotter, calcium carbonate wants to come out of solution. This job is not easy, folks. We are heat transfer efficiency managers, meaning that we are dealing with heat, and the water treater's nemesis is calcium carbonate, and the hotter it gets, the more it wants to come out of solution. Now, most things want to go into solution the hotter they get, but calcium carbonate does not do that. It does the inverse effect. Now, if you're wondering what I'm talking about, and you ever had Georgia sweet tea, you know exactly what I'm talking about. Now, the great state of Georgia, where my home is, we have this incredible elixir called Georgia sweet tea. And I know what you're thinking. You're thinking, I live in Indiana and we've got sweet tea. Folks, if you are not in Georgia, you have no idea what sweet tea is. Now, sweet tea is very special in Georgia. There's a secret recipe for it. And then there is so much sugar in the sweet tea, it's guaranteed to rot at least 2 or 3 teeth with 3 sips. I think that's in a standard somewhere. Folks, when I talk about this, I always ask people, how do we in Georgia get so much sugar dissolved in that sweet tea? And they always tell me, well, you have to get it hot, and then you put all that sugar in while it's hot, and that's how it goes into solution. That's how most things are. The hotter we get things, the more we can dissolve in a liquid. Calcium carbonate is the reverse. The hotter it gets, the more it wants to come out of solution. So it's very important we understand what our water is telling us, what products we're putting in the system, making sure those things match up so we can keep the system clean as heat transfer efficiency managers. So what are some of the tools that we use to help not scale up a system? Well, folks, if you have a cooling tower, I guarantee you have a bleed set on that cooling tower. Now, my father used to say the solution to pollution is dilution, and what he was saying only pure water evaporates, leaving its solids behind. And eventually those solids reach a point where the water can no longer hold those solids in solution, and then they precipitate out and they form scale, and that becomes that insulation that we do not want. So what we do is we do water tests. We figure out what's in the incoming water and how it's concentrating up in the system that we are treating. We then figure out which ion is going to scale first, and then we're going to set a conductivity bleed so we never get up to that situation. We never get it up high enough, so we create a scaling situation. And through the adage, the solution to pollution is dilution, we open up a bleed valve, we bleed out that heavy concentrated solids water, and we replace it with the not as concentrated at all, not concentrated makeup water, so we can dilute that out. So that is what bleed is doing. I know you out there in the Scaling Up Nation already know that, but you also know that our job is not only to prevent scale from occurring, but to do it in a way where we're not wasting the water that's going down the drain. I can't tell you how many customers I've talked to or even seen close the bleed valve because they didn't want to waste water. They didn't understand what we were trying to do, and that was an issue with us not explaining what they needed to know about their system. Once we had that conversation, we didn't have that problem again. But I have also seen water treaters where they have not done their due diligence to figure out how can they maximize that bleed set point and not waste any of that valuable resource, not waste any more water than they need to, and keep the system clean. So folks, if you do not know which ion is going to come out of solution first, or you're going to have a problem with, you need to run some tests and you need to ask some questions. Now, depending on which product you are using, you will have special limitations. Now, I can't tell you those, but your technical directors can. They know what's in those products and they have tested them, And they're going to say these are the 6 things that you need to test for, and whichever one is going to occur first, that's going to be your limiting factor. You're then going to multiply how many times it's going to take to concentrate up in your raw water and multiply the conductivity out by that, and that's going to give you roughly what the conductivity set point needs to be. Now, I said I have personally seen where water treaters have not done a very good job of extending the amount of water in their system, and they will overly bleed the system. Well, here's some math, folks, and it's not hard math, but you can very easily see how much water you are wasting by using the reciprocal of the concentration ratio. Now, what the heck did I just say? Okay, well, we all know what the concentration ratio is. If I concentrate something up 6 times, then my concentration ratio is 6. Well, the reciprocal is just a big fancy word that means I'm going to create a fraction by putting 1 over 6. And then whatever my makeup is, I'm going to multiply it out by 1/6. So with that, let's say we're using a 200 gallon per minute makeup, and we're going to divide 1 into 6, so that equals 0.16. That's a coincidence, as it doesn't always work that way, so please do the math. And then I'm just going to multiply across. So I take my 200 gallons per minute makeup, multiplied by my 1/6, the reciprocal of my concentration ratio, and I find that out of that 200 gallons a minute, I am bleeding 32 gallons per minute. Makes sense, right? And that's probably not a bad concentration ratio for most places, but what if that's what they could run and they were only running a concentration ratio of 2? Well, 1/2, if we divide that out, that would be 0.5. So if I multiply 200 by 0.5, we would be bleeding 100 gallons per minute. Folks, that's a big difference between 32 and 100 gallons, and that's wasting water. That's making the customer pay for more water that they do not need to pay for. It's possibly making them use more water, graduating them up into another tier. So now every drop of water they pay for is more expensive. But folks, you listen to this show, you know there is a finite amount of readily available water on this planet. And us as water treaters have the ability to save more water than most people combined. We're not doing our job if we are not utilizing things like this. So please, let's be good stewards of the water that allows us to practice our craft, to do what we do, to get a paycheck, and to make all the friends and things that we do on a regular basis. If we're not able to use water because it's not available to us, we are going to have to find a new job. And folks, I love this job too much, and I don't know what I would do if I was not a water treater. So let's make sure we are all doing what we need to do by saving water. Now, all of that was meant to express how important it is for us to properly set up the bleed on a system. Again, the solution to pollution is dilution. That sounds sort of goofy. My father used to say that. I thought he was goofy when he said it, but it makes perfect sense. That's why we bleed the system. And then we look at the 5 components that make up calcium carbonate, and then we can do something with each one of those to reduce the likelihood that we would scale. So we might want to control pH, and you might have a system out there that's using acid to suppress the pH. You might have a water softener that takes the calcium out of the water. Maybe you have a dealkalinizer and you're taking some of the alkalinity out. So whatever we are doing to take away one of the 5 components, and we're probably not going to do anything with heat, and with conductivity, we talked about what we can do with that. That's how we're managing our bleed. So the only real other ones that we can look at are alkalinity, pH, and hardness. So if we do something with that, perhaps we can extend the concentration ratio. Now, there is a far different water quality in Florida and Georgia. They have much harder water, so they might have to actually use acid. We don't have to do that up here in the Atlanta area. So with all of that, you have to know what water you are treating so you approach it correctly. So let's get into our special sauce, and that is the products that we use to inhibit scale formation. So I talked about this a couple of weeks ago, but I'll do it again. As we concentrate, pure water evaporates, leaving its solids behind, and we get to a point where there's so many dissolved solids in the water, we are not able to hold them in solution. Actually, it's the water doing the work. The water cannot hold them into solution, and they create a seed crystal. We call that nucleation, and that crystal begins another crystal, which begins another crystal, and you get this domino effect, and those crystals grow into what we see as scale. So knowing that, we have a couple of different items that we can throw into the system via our special sauce, via our products, and all of those products combined we call deposit inhibitors. And we can do deposit inhibition through three mechanisms: threshold inhibition, crystal modification, and dispersion. So let's talk a little bit about each one of those. So threshold inhibition, if I can keep X amount of a certain product, let's say calcium. So how much calcium do I have in the system? I then test that, and then I'm going to look at my technical data sheet to see how much water that I'm using with this product can hold in solution. And let's say with using this product, and it has this threshold inhibition agent in it, we can now extend what the water would naturally hold in solution 10 times out. So maybe we were only able to hold X, now we can hold X times 10. So we are extending the threshold that the water is able to keep in solution because of the threshold inhibitor that we're putting in there. The next thing that we might use is crystal modification. Now, folks, if you have ever seen an electron scanning microscope picture of calcium carbonate, it is really cool. It is a perfect square. And what do squares do? What do boxes do? They stack very well. That's why we can scale up a system overnight, and it takes so long for us to clean it up. It packs in there so tight because of the way that that crystal grows. So what we can do is we can add an agent that when it comes out of solution, it will distort what that crystal comes out at naturally. So instead of now a box, it's now going to be a sphere or something distorted that kind of looks like a sphere. So it rolls around more instead of stacking. That's called crystal modification. Now, the last thing in our scale inhibition bag of tricks is dispersion. So dispersion is the process by which we add something and it doesn't allow particles to come together. So instead of particles combining, what it's going to do, it's going to give them all the same charge. It's going to give them all a negative charge, and like charges repel each other. So they don't want to come together. So by using a dispersion agent, that's what that does. Now, Bruce Ketrick says something that I love. It's not technically correct, but it really allows it to make sense. He says that dispersants make it so slick so it don't stick. And I like that. But again, really what it's doing, and he knows this, he just thinks it's clever to say it, is that we're putting a negative charge on everything so it's repelling each other so that way it doesn't stick. So those are the three mechanisms that we can use to inhibit scale formation: threshold inhibition, crystal modification, and dispersion. Now, if you look at your products and see what they're made up of, you might see some phosphonates. So phosphonates might be ATMP, HEDP, PBTC. You might also see some polymers. Those are the acrylic acid, the AA amps, the malic acid, and the phosphinocarboxylic acid. Now, putting those things together is probably what's going on in your products, and those are crystal modifiers and threshold inhibitors. They actually do both. And we will see some do things better than another, and what we'll do is we'll blend a couple of those together so that way we get the best of both worlds. So I'm asking you, if you're unclear about this, go to your labels, go to your technical sheets, go to your safety data sheets, and review some of the names that I just mentioned. Again, they're either going to be phosphonates or they're going to be polymers, and you will see that that's what's in your product, and now you know what they are doing. As far as dispersions, we might see the polyacrylates, we might see acrylates, we might see amps, we might see terpolymers, we might see, and by the way, a copolymer is several polymers. Polymer means many, and co means we've got several of the many. So sometimes you'll hear people say terpolymer or quad polymer. You can say that, but you're just wasting your time. They're all copolymers. They might have some different chains to them. And then some of them might even have a styrene on the end of it. And you're like, well, what the heck is that, and why do we have that? Well, typically, manufacturers will add that because that does a good job of helping us transport iron. So I throw all these big names out. Not that I expect you to remember them, but now that you know about them, you can look at your products and you can begin to understand your products better. And if you're a water treater that is treating water in a large area, you might have products that work very well in one part of your territory and will fail miserably in another part of your territory. We have to know what the water is that we're going to be concentrating up, and then we're going to match the proper products to that water. And somebody in your company has already done the legwork to figure out, okay, what kind of dispersants, what kind of threshold inhibitors, and then what kind of crystal habit modifiers do I need to throw in the mix to treat this type of water, and then how much to treat this type of water. So make sure you understand what you are doing, because if you do not, the results can be disastrous. Folks, I have been called in on many occasions where something disastrous has happened and a fellow water treater couldn't figure out what was going on, and they were simply using the wrong chemistry. So it seemed to have worked for a while, but they weren't able to see what was going on internally in the system, and what they thought all of a sudden took place overnight was actually taking place over the entire past year. And then they saw a result where they weren't monitoring, the customer wasn't monitoring like they should, that it just would not cool anymore. And in the specific instance that I'm thinking of, they actually had to comp an entire hotel because the air conditioning did not work properly. Folks, do you think that customer was happy? Absolutely they were not. We were able to help them get the product that they needed after we cleaned up that situation, but nobody was happy. Luckily, we were able to help that client. So how do you know if a chiller is scaled up? Well, folks, earlier in my podcasting career, I interviewed Mark Lewis. It was around the 30s. I don't remember the exact number. If he was here, he could tell you exactly which number it was. But Mark went into how to look at a chiller user interface and figure out what's going on with the chiller. And I can't tell you how many water treaters that I've spoken with that are terrified to go up to those chiller user interfaces to get data off of. Folks, if you are uncomfortable with that, ask somebody who really knows the machine. If you know a chiller tech very well, they would love to share their expertise with you and show you how to navigate that. But you can then pull off data where you now have proof that you're either maintaining the same efficiency, or it's getting better, or maybe it's even getting worse. But now you can do something about it instead of waiting for the customer to say, it's not cooling at all, and my manager had to comp every single room in the hotel. So there's data out there. We just have to use it and make sure that we're making decisions with it. Folks, there is no doubt about it. I love being a water treater. I love taking a water sample, learning what's in it, and learning the equipment that water is traveling through, and making sure that I create the best plan that I can to keep that system as energy efficient as it can be, to minimize the corrosion that is taking place in that system. Now, as a water treater, we also have to make sure we're keeping the biological loading at bay, and then all the dirt and debris that's coming in the water or getting scrubbed out of the air. If it's a cooling tower, we've got to do something with that as well. In an upcoming episode, I'm going to be talking more about what the difference is between a Legionella prevention program and a regular microbial program. The short of it is that our job as water treatment professionals is to make sure that we do not grow microbial activity in the system at a rate that retards heat transfer, or it doesn't allow our products to get to the metal surfaces. It is by no means making sure that the system is sterile or eradicating a specific species. We're going to be talking specifically about Legionella on some upcoming episodes, and as you know, I've already spoken with other people on Scaling Up H2O about Legionella. So if you want to check out those episodes, I highly recommend that you do that. Folks, early in my podcasting days, episode 9 was when I interviewed Janet Stout. And Janet Stout is coming back on the show a little later, and she will tell us even more about Legionella. But if you want to learn about Legionella, episode 9 is a great place to start. And if you are wondering what the differences are between a regular water treatment program and a due diligent Legionella prevention water management plan, then you should listen to episode 83. I interview Matt Farigi, and he tells us exactly what the differences are and what we should be prepared for to have that conversation with the customer. Now, earlier in the show, I mentioned the ones about Mark Lewis, and those were episodes 31 and 34. I cannot remember which one he talked about the chiller, so you might have to listen to both of them to find that. I think it was 34, but we had a lot of fun on that episode. And if you haven't listened to that episode, Mark actually came to my office to record the episode. And if anybody knows me, you know I like to have notes and I like to have things planned out. So not that we have a script, but I have a list of questions so I can make sure that I keep the conversation going so you, the Scaling Up Nation, gets the information that you need. Right before we turned on the microphone, I asked Mark if he needed anything, and I was thinking like a glass of water, a more comfortable chair, something like that. And he said, yeah, give me one moment. He reaches over, he takes my notes, he crumples them up. He then throws the crumpled up notes over his shoulder and goes, now I'm ready to start. So that's what I had to deal with on that episode. And folks, if you haven't figured it out, Mark Lewis and I are great friends, and we would not have met had we not shared a love for the water treatment industry. And because we were both involved in an industry association, we were able to meet. And because we volunteered together, we got to know each other, we got to appreciate each other, and now we are excellent friends, and we make sure we become better water treaters by continually challenging each other. So folks, your job, in addition to understanding what you are doing on a regular basis, what is in your special sauce and why you need to put it in one type of water and not another, you also need to make sure that you're involved in whatever trade association allows you to meet like people. When you do that, I promise you will have more fun because you're no longer an island. If you have not gone online and searched what industry associations are available to you, I highly urge you to do that. Well, Nation, I again want to thank you for your questions. Because of your questions, I have information to do podcasts. I am able to send to you the right shows that you want to listen to. And it's my hope that when you listen to these, it does encourage you to learn something new. It encourages you to do something a little bit different, thereby making you a better water treater. Folks, if you're not better tomorrow than you were today, I'm going to have you consider that you're maybe not doing this job correctly. And if you stay stagnant too long, I promise you this job can get boring. I've seen it happen to so many people. And I have never been one of those people. I have never been bored in this job because I always am trying to push myself by learning new things, by meeting new people, by doing things a little bit different to see what the results are. And I've seen many people that just stay stagnant and then they decide they no longer want to be in water treatment. Don't be that guy. Don't be that gal. Make sure you take advantage of everything the water treatment industry has to offer you. One of the cold, brutal facts as being a water treater is we do not have time to do the things that we need to do to make sure that we are educating ourselves. So folks, it is imperative that when you find something that you can educate yourself on, like maybe this podcast, you take advantage of it. Maybe you're going to an industry association's technical training that allows you to take information and then take it back into your field if you do it properly. Now, I've done several shows on how to do those technical trainings properly, but now it's up to you to get there and do that. Another thing that you need to do is to make sure you are keeping your mind sharp. And I think the best way to do that is to read. Unfortunately, we can't read until we're at home, and as a water treater, we do a whole bunch of driving, and even though I have seen it on the Atlanta highways where people are reading a book while they're trying to steal their car, I hope nobody in the Scaling Up Nation is doing that because that is just not smart. So how do you read while you're driving? Well, you already know the answer. That is Audible. And folks, I can't tell you how much I love Audible. And I can't tell you how many people in the Scaling Up Nation have responded back to me to let me know that Audible is indeed that awesome tool that I say it is because they're now able to read. Now, whether it's a water treatment book or it's some Tom Clancy story, it still allows you to read. Now, my hope is that you're expanding your knowledge in water treatment, but if you're reading, you are reading. So by all means, check out Audible. I can get you a free book and a free month by going to scalinguph2o.com/Audible. And I would love it if you could tell me what you think about it because I'm pretty positive it's going to allow you to read again. Nation, you know I can't end a show without asking you to continue keeping those questions coming. So if you have an idea of what you want me to talk about, or you have a guest that you want me to interview, let me know. You can do that in several ways. You can go to scalinguph2o.com and go to the show ideas page and just type in exactly what you are thinking. Another way you can do it is as soon as you go to scalinguph2o.com, you will see an orange icon on the right-hand side of the screen, and you can record a voicemail to me asking your question. Now, here's the cool thing about that. If I use your voice on the air, you will get a Scaling Up t-shirt. So folks, who doesn't want a Scaling Up t-shirt? If you go to an AWT event, you are going to see many of these Scaling Up t-shirts, and people love them because it just is fun and it's cool to wear. So make sure you get yours. Make sure you are keeping that information coming to me. And my ask also is that you share this podcast with other water treaters. The bigger we get the Scaling Up Nation, information, the better the information is going to be, and we're actually going to be able to make the water treatment industry better. Folks, thank you so much for listening to Scaling Up H2O, and I will talk with you next week.